Bryan received his bachelor degree in aerospace engineering at UT Austin in 2008. And then he received his master's in aerospace engineering in December of 2010 from UT Austin. And during that time, he spent time during his master's analyzing different types of remote sensing data to assess natural hazard environments. On the summer, towards the end of the summer in 2011, he joined the Seismo Lab as a PhD student. And in 2012, actually Bryan was awarded a NASA graduate fellowship. And in that same year, he received the AGU, one of the AGU student presentation awards. And during his time here, he's really taken geodetic data analysis to an entirely new level. And he will be, actually this month, he's accepted an offer at JPL where he'll be joining the remote sensing section of JPL, the radar science, as a signal analyst engineer. So without further ado, I'd like to give the stage over to Bryan.
Thank you, Jennifer. Thank you, everyone, for coming here after a long weekend. So today I want to talk to you about part of my thesis work, and the title of the talk would be Automatic Decomposition of Geodetic Time Series for Studies of Ground Deformation. So I want to start off and go straight into an illustrative example of why geodesy is helpful for geophysicists when we want to study Earth processes. So imagine you have a caldera that's sitting on top of this idealized magma chamber, as you can see there. And this magma chamber is dormant, and this caldera is subject to, let's say, cyclical up and down motions, perhaps due to earth tides. And if we have a single GPS station sitting in the middle of the caldera, we measure noisy observations. Then at some unknown time, the magma chamber inflates in a transient inflation event. This becomes reflected in the elevations that we see here. We get a transient uplift. And so the next step would be, okay, I have a single point on the ground that measures this transient event, but I want to get a better idea of the spatial extent of this process. Can I get a better idea of the physical properties of this chamber? So you distribute more GPS stations. And let's say we have 3 GPS stations. And when you do that, the caldera still goes up and down, let's say due to earth tides. We make noisy observations, and then at some unknown time, we get a transient uplift event in these 3 stations. And the magnitude is actually different for these 3 stations depending on where they are in the zone of uplift. And so now we have a better idea, perhaps, of the depth of the magma chamber or the size. So to get even more sophisticated, you say, okay, 3 is not really good enough. I want to get a good, solid distribution of stations around the caldera. So at this point, you have, let's say, 25 GPS stations making 25 noisy observations. At some unknown time, we get a transient uplift event where the magnitude is spatially varying across your stations. So now you get a better idea of the spatial properties, but now you have more work to do. You have 25 stations to look through manually if you wish. And let's say if you want to take the horizontal components, then you have 3 times as many data to look through. And then someone says, you know what, we can actually do a really good job if we have INSAR time series. So INSAR would give us spatially continuous satellite-based observations of ground deformation. And so when we do that, we have we can measure both the periodic effects and as well as the transient uplift event. Now we have 1 million data points instead of 25. And now your work became much, much harder. How do I track 1 million data points, and how do I track their temporal evolution automatically and quickly in case this thing presents some kind of natural hazard? So the outline of my talk will be, first we have to define what are transients. I used the word transient several times. How do we detect them? If you're going to hunt for treasure, you kind of want to know what the treasure is that you're looking for. And after we go through this definition, we'll develop an automated transient detection algorithm for 1 time series or n time series, 1 or many. And then to do many time series, we're going to develop a large-scale time series analysis for INSAR time series. And in the latter half of the talk, we're going to apply this to INSAR and GPS data over to Los Angeles groundwater basins. So these groundwater basins are deforming in a very complex manner due to groundwater pumping effects. And so the main goal here is we want to quantify the extent of surface deformation due to groundwater pumping. Can we use more sophisticated methods to get more information about these hydrologic effects? And then we'll compare surface deformation to aquifer pressures to study groundwater dynamics. So, first of all, what are transients? So here's a real-world example of a volcano in Alaska. Similar to the example that I showed you earlier. Let's say we have GPS stations distributed around this island. And over a period of maybe half a year, all the GPS stations exhibit this this uplift event starting around 2008. And you can see it in the horizontals as well. And so they have this spatially coherent motion. And in this particular paper, what these authors did is that they used statistical-based methods. They looked for temporally and spatially correlated signals in the data, but without knowing anything about the physical process itself. So you're looking specifically at the statistics. You're agnostic to geophysics or anything like that. You just want to look at the data itself. And one of the main techniques that's used for this is called principal component analysis. You may have heard of that. Other techniques include independent component analysis, which has come out recently, which kind of overcomes a lot of the limitations of PCA. On the other side of the spectrum, a lot of transients that happen, that occur, that we observe, we do know what the process is. So one of the most famous examples are these slow slip events in the Cascadia subduction zone. You have these slow earthquakes that have propagating slip that occurs over a period of 2 to 3 weeks. And so in this case, you can use physics-based models. In this case, you would use elasticity to constrain the spatial pattern of the transit, so you know what the spatial signature should be that you're looking for. And then to model the temporal evolution, you can go with a parametric approach. If you know it's a steady evolution, you can use linear. Let's say it's something like post-seismic decay, you can use an exponential function. But if you don't know what the temporal evolution is, you can use non-parametric methods. And maybe some of you might know about the network conversion filter, which is based on common filtering approaches. So now you get this transient detection workflow, where if you're given a data set, you start off at this question. Is this a known geophysical process? If yes, then I can specify a physical model for the spatial properties. And do I know the temporal evolution? If yes, then I can parameterize it. If not, then I'll have to use something non-parametric, like a network conversion filter. If I don't know the geophysical process, then I have to use statistical models, statistical methods, so just purely examine the data. What we want to do is we want to take something that kind of differs from these two paradigms. We say, no, we don't necessarily know what the geophysical process is, but we do know that transients often have several known properties. We know that they're non-repeating. They have a characteristic temporal pattern. A lot of transients we see have these slow step nature in time. And we also know that they're spatially coherent, that the transient signal should have a finite extent in space. And so all these three characteristics are very important and would aid us in detecting these signals. So what are transient signals? We define them as a surface manifestation of non-repeating geophysical processes. So basically that means these are signals that they're not secular, they're not steady like plate motion, or they're not seasonal. They're not these seasonal effects that you would expect to occur regularly. Some examples of transients are slow slip events, volcanic activity, inflation, deflation, or hydrologic effects, which we'll see when we look at the LA Basin, and many, many others. So to develop an automated time series analysis, we first approach a single time series for one station. We don't know where it is, we just have time series. And we want to develop an automated transient detection method for this time series. And what we do is we cast the detection problem basically as a temporal decomposition problem. Can we decompose a time series into its main constituents? And to illustrate that, let's say we have this full signal here as we observe. We can break it down into a secular component, a steady term that could be due to something like plate motion. We have seasonal effects, as we can see here. And then also we can have any number of transient effects. In this case, you can see an acceleration of the data right around the middle, which would correspond to this transient event. So since we don't know what the physical process is, we have to use flexible time parameterization. We can't use something that's based on a model. So what we do is we use these generic mathematical functions that resemble transients. In this case, these are third order integrated B-splines. And if you look at them, they look a lot like the transients that, of the examples that I showed you. And what you can do is we can construct these B-splines so that they have any number, any size of duration, and any magnitude. So it can be very flexible in where we put them in terms of reconstructing the signal. And so what you do then is that you then build up a dictionary or a database of functions, of all the functions that you think could be in your data. So here you want to be safe. You want to be as generous as possible. You put all the signals that you think could be in there. So in this case, we build up this dictionary or a giant matrix where in each column we have what we think could be in the data. So we could have some secular effects, some seasonal effects. We could have very rapid transients at any given onset time. It could happen anywhere. Or we could have a medium duration transient or these long-term transients. And so what happens then is that if you assign a coefficient to each one of these elements in your dictionary, and you place those coefficients in this vector m, you do a linear relationship, g times m, to reconstruct your data that's stored in your vector d. So to give you an example, let's say I have 32 of these integrated B-splines, and they're evenly spaced in time. They all have the same duration, they're just at different onset times. And I'm going to select 2 of these to be non-zero. And so this color representation is the color representation of the coefficients for each one of these splines. And so you can see that white is 0, and I've given a positive value to this spline and a negative value to this spline, so that I can create a synthetic signal that looks like this in black. Perhaps this is an uplift event if you're looking at elevations, and then we have some subsidence. And then I'm going to add some noise on top of that to resemble some kind of realistic time series. And so the transient detection is then solving a least squares problem. You're trying to solve for m. So in this case, if you use ordinary least squares, though, what happens is that if your cost function is only minimizing the sum of the squares of the misfit, you're going to get a very noisy reconstruction because G is very ill-posed. It's non-orthogonal, highly redundant. And so when you try to do like a pseudo-inverse of it, it's going to be poorly conditioned. And so this gets manifested in the reconstruction. If you look at the red time series, red reconstruction, you can see it's quite noisy. And if we look at the coefficients, this is really telling right here. We see we have these high trade-offs, positive, negative, in the estimated value of m, because it's trying to hit every wiggle in the noise. And okay, so to take one step, to do a little better, you can use regularization. We know that these values shouldn't be fully unconstrained. We want to kind of minimize the size of the vector m when we know that G is ill-posed. And so usually what you see in science is you take the L2 norm, you have a joint cost function where you add on a penalty for the L2 norm, which is the sum of the squares. And you can see that the reconstruction is a lot better. It's smoother, it's not as noisy. And if you look at the coefficients, you can see that there's not as much trade-off, but it's still not that good because you have kind of like a spreading out of energy of the true coefficients here. And so what we do is we say we don't want to minimize the size, the L2 size of this. What we really want to do is we want to minimize the total number of dictionary elements that we need to reconstruct the time series. We know that we only need just a few of these things that are in our dictionary to be able to reconstruct the time series. So what you do then is instead of using an L2 norm, you use what's called the L0 norm, which is called the counting norm, which tells you how many non-zero values do I have. Unfortunately, that's a very hard problem to do on a computer. It takes a lot of combinatoric math, and it'll take you thousands of years to solve. Fortunately for us, we can use convex relaxation to replace the L0 norm with an L1 norm, where the L1 is the sum of the absolute values. And if you think about it in a probabilistic manner, the L1 norm is essentially, well, it is exactly Laplace prior on your coefficients, where you have a prior belief that the coefficients should be close to 0. That's what the Laplace is having a high probability for coefficients at 0 as compared to a Gaussian prior. But it also has long tails, so you can allow for a sparse number of non-zero values. So it has a lot of the same properties that we want of the L0 norm. So when we use the L1 norm, what happens is that we get very good reconstruction, almost perfect reconstruction of our input signal. And if we look at the coefficients, we see that everything that doesn't contribute to the data fit is zeroed out, and we isolate just the two transients that we wanted to. So that was for one time series. So how do we extend this to multiple time series, for time series in a GPS network? So we know that transient signals should be spatially coherent over a finite region. So spatially coherent means that there should be common non-zero B-splines for neighboring stations. So if I'm a station sitting on top of a caldera, I know that the station nearby should have the same set of non-zero splines as I do, because this uplift event is affecting us both at the same time. So we should have a consistent solution between a finite extent of stations. And so what we can do is we can use an iterative reweighting approach, where we perform sparse estimation independently for a GPS station, and then we do an intermediate step where we apply a spatial weighting scheme that penalizes B-splines that aren't persistent over multiple stations. So if I'm a station and I really want to choose this spline as a transient, but no one else is seeing it, it's probably something that only I'm seeing, and it's not something that we are interested in as geophysicists. So this spatial weighting scheme will penalize those, and then we can redo the estimation with updated penalties. So to illustrate that, let's say here are 5 GPS stations. This is real data over the Long Valley Caldera in California, which experiences these episodic uplift and subsidence events. And if you look at the raw data, you can see we have these seasonal effects, perhaps some long-term secular motion, and a transient inflation event. So now if we apply the transient detection that I described before with the L1 norm, and isolate the transient signal, we see that we've removed a lot of the seasonal effects. But if we look at the reconstruction of the transient, which is shown in red, you can see that there are a lot of signals here that are mainly local to each station, that aren't spatially coherent, like you see here. You don't see it in the neighboring stations. And so it's not spatially coherent, and it's probably local effects. So once you apply the spatial weighting, you see that you're able to isolate only the part of the transient that is coherent. And in this case, that part is due to the inflation. We have this inflation and then deflation after the magma chamber decreases in pressure. Okay, so that's all well and good, but how would we apply this to INSAR? Let's say we have INSAR time series. So the difficulty with INSAR is that instead of discrete points on ground, you have continuous maps of deformation. So INSAR works, the way INSAR works is that it's an active radar imaging system where it emits microwave radiation to the ground, and it records the amplitude and phase of the returned waveform. And so the amplitude is proportional to the strength of the backscatter of the ground elements, and the phase is proportional to the range between the satellite to the ground. And so for one image, the phase looks quite random because it is random. The distance, the range change should be quite random. But if we fly through and come at a different time, let's say 3 months later, we measure amplitude and phase, and we're at roughly the same viewing geometry as before. The magic happens is when we subtract the phase terms from each other, what happens then is that you get a range change. So each one of these is proportional to range, and any change between these two time periods will be shown in the change in range in this interferogram. It's called an interferogram. So you get these coherent patterns of deformation. In this case, this is Los Angeles, and so you can see something that might be due to groundwater basin subsidence. Unfortunately, range change can also be due to atmospheric effects, orbital noise. So, every instrument has its own noise source. And so luckily, when we have most time series methods try to reduce these effects by trying to isolating the deformation signal. So to apply transient detection for INSAR time series, we can basically treat INSAR time series as a dense network of GPS time series. And so you can apply the exact same methods that you did with GPS onto INSAR. So in this case, each pixel you can call a GPS station. It's measuring one component of deformation along the line of sight direction. And so then you have time series for a million pseudo-stations. So you can perform sparse transit detection on a pixel-by-pixel basis, and then you can do spatial sparsity weighting to isolate the signal that's coherent over a region. So without going into too many details, you just have to trust me that that's actually quite a very expensive operation to do. It works for GPS, but it completely blows up for INSAR. So what we can do instead is we can do a simultaneous inversion of all the pixels. By meaning that instead of doing this iterative method, we solve for the m vector for all the pixels all at once. So for n pixels, for k interferograms, what you're going to do is you're going to construct an extremely large least squares problem. You're going to take all your interferograms, stack them on top of each other into a giant vector D, and then you intelligently construct your G matrix for each pixel so that each pixel has its own dictionary. As you can see here, each pixel is going to have its own dictionary, and then this partitioning is representing the partitioning of the interferograms. And so now we get an m vector for n pixels. So of course, this is a very, very large least squares problem. And so what we want to do is we want to use our sparsity regularization as before, but we have to take care into enforcing the spatial coherency. So something that we can use is what's called elastic net regularization, which combines L1 and L2 penalties with a smoothing matrix. So first of all, you have the sum of the misfit term, your likelihood term, then you add in the L1 term, which is a sparse number of coefficients, and then you just simply add on an extra penalty, an L2 term, which penalizes the smoothness of your reconstruction. So for a given spline, its spatial distribution should be smooth. And so now you have a least squares problem that has joint misfit, L1, and L2 penalties. And the advantage here is that with this method, it's been proven to show that you can select groups of correlated coefficients, sparse groups. Instead of just choosing one, you can choose a group, but still maintain sparsity. And then this group is then representative of a spatially coherent transient event. And this allows you to, and this framework also allows you to have more flexibility in enforcing correlations between model parameters. So in this case, S is simply a smoothing matrix, but you can also create S to have to include covariances that you would expect in time. Let's say you have a propagating signal. You can construct S intelligently so that you can enforce this propagation nature. And you can also apply a full data covariance matrix here in your likelihood term for a more accurate error model. So for large data sets, the memory requirements make it very, very hard to perform, basically impossible to perform on a single computer because it scales as n squared, where n is the number of pixels. So the solution then is to split up the problem among many, many computers. And the approach that I used is a distributed convex optimization algorithm called alternating direction method of multipliers. It's a fancy name, but basically all it does is that it takes your giant least squares problem and chops it up into bite-sized bits and solves each bite-sized bit independently, and then it coordinates it algorithmically to estimate the global solution. And so there are different ways to partition your data, and the one we're going to use here is we want to partition by the parameters. So each processor is going to get a chunk of the global solution vector. In this case, I'm showing each processor would get a pixel. So then it would get a chunk of the global vector, and then it would also get a corresponding chunk of this giant G matrix. And so then you can get something, if you have hundreds of processors, or even thousands of processors, this is something that you can solve in a matter of minutes as opposed to hours if you wanted to take the traditional approach. So I will show you how this works in the next part, where we're going to talk about how do we apply these methods to INSAR and GPS data over LA groundwater basins. So to set the stage, here is the area that we're all familiar with. This is our home. Here's Los Angeles. And what we're focusing on here are these basins here, these groundwater basins that are filled with alluvium that can store water in their pore spaces. And so and groundwater pumping actually contributes to a lot of the water that we use for drinking and everyday use here. So these are very important. So in this case, well, we're going to be focusing on the Central Basin and the Santa Ana Coastal Basin here in Santa Ana. And if you look at the tectonic setting of LA, many of you are familiar with, we have lots of faults. And in this case, the one that we're going to be highlighting here is this Newport Inglewood Fault. And it's going to act as a very strong barrier to fluid flow, as we'll see in the next few slides. And I also want to point out this red line here, which is separating these groundwater basins into two different areas. One is called the forebay, and one's called the confined area, or sometimes called the pressure area. So the forebay is where the aquifers that are in the groundwater basins are unconfined, and the pressure area is where they're confined. So what does that mean? So for a given groundwater basin, let's say you have an unconfined aquifer sitting on top of a confined aquifer. For an unconfined aquifer, as you add water to the aquifer, the water table is able to move freely up and down, so it doesn't have any confining pressure. For a confined aquifer, you have this confining stratum here, what we often call aquitards, which are made up of relatively impermeable materials, such as clay, which has a lot lower permeability than sand or gravel. And so what that does is that when you add water to a confined aquifer, you place it under confining pressure. The water is not allowed to move freely up and down, so it's under pressure. And so if you use a monitoring well to monitor water levels, for an unconfined aquifer, what you measure is directly the water table. For a confined aquifer, what you're actually measuring is what's called the piezometric surface, where the hydraulic head is then directly proportional to pore pressure. So this is very useful. By measuring hydraulic head, we can measure pressure of a confined aquifer. And to be a little more realistic of the geometry of the aquifer system that we have in the Santa Ana area and the LA area, is that here in Orange County, they developed a 3-layer system where there's a shallow aquifer, principal aquifer, and a deep aquifer. So this is a good approximation to the aquifer structure in these basins. And we also have, and as before, we have a line here that partitions between pressure area and the forebay. So in the pressure area, all 3 aquifers are confined. They have, you add water to the system, and then the pore pressure changes. In the forebay, the shallow aquifer is unconfined. So this is where you do most of the recharging operations happen. This is where water districts put in water into these seepage ponds that are allowed to percolate down into the confined aquifers. And also, if there's rain coming down from the mountains, it will enter through this unconfined area and seep down into these aquifers. And so most of the pumping is done in the principal aquifer. 90% of groundwater pumping is taking water from the principal aquifer because it has the highest storage. And also the deep aquifer contains what's called amber-colored water, which is basically really ancient wood and decayed carbon material we don't want to drink from here. It's pretty nasty. So, but there are still pressure variations in the deep aquifer. So how does this relate to ground motion? We know that ground motion is due to the integrated compaction of multi-aquifer systems. So as each one of these aquifers compacts, let's say we take water out of it, it compacts, you get ground deformation. And so integrated means that they all compact at the same time. Well, not at the same time, but they will all compact. So to show you that, let's say we have our shallow, principal, and deep aquifer, and we put in a production well here, and we're going to pump from the principal aquifer. And as we pump water out of the principal aquifer, we reduce the pore pressure, so we increase the effective stress on the sand and the gravel here, on the matrix, and so that causes it to compact. And then what happens then is that all these layers compact because water will flow due to pressure gradients. Water will flow to the well, and so you get compaction of all the layers. And so the integrated compaction is what you measure as ground subsidence. What you measure doesn't know the partitioning of the compaction for each one of these layers. It doesn't know anything. All it knows is that we have this total subsidence here, and it's due to the integrated compaction of these aquifers. So basically to relate the relationship between hydraulic head change and ground deformation can can be derived using the principle of effective stress, which basically says that effective normal stress, where effective normal stress is the difference between normal stress and pore fluid pressure. Changes in effective stress are linearly related to changes in hydraulic head. And so it can be shown then that you have a very simple linear relationship between a change in aquifer thickness, delta V here is a change in aquifer thickness, that is linearly related to changes in hydraulic head under certain assumptions. So you have this elastic, basically an elastic relationship between pore pressure or hydraulic head and aquifer compaction. So then what we want to do is, if we know that that relationship should be elastic, what we can do is we can partition the data. We want to look at signals at different time scales. So we want to look at short-term signals and long-term signals separately. The reasoning for this is that because short-term signals, which are mainly driven by short-term aquifer pressure changes, seasonal variations in pumping, recharge, these are short-term changes in pressure that should be elastic. We shouldn't see something that's causing inelastic effects. So we can look at this separately. And then we can also look separately at longer-term signals. So these would be driven by longer-term aquifer pressure changes, such as accumulated overdraft, or perhaps drought conditions like we see now, lower availability of water. Or we could also see delayed inelastic compaction. So inelastic compaction occurs when we take out too much water from the system, and materials like clay, the effective stress will exceed what's called the pre-consolidation stress. And so that you'll get this permanent rearrangement of the grains, and you'll lose a certain storage permanently for that layer. And so this effect is delayed. It behaves logarithmically, and it usually occurs over a time scale of several years. So we're going to be on the lookout for these signals when we look at the long-term signals. So to start off with, we want to look at we want to look at hydraulic head levels throughout these groundwater basins and compare it to ground deformation. So the WRD, which is the Water Replenishment District of Southern California, they manage groundwater in LA County, and they have 55 monitoring wells throughout the basin. But here we're going to only use about 12, I believe. And Orange County has 400 monitoring wells within the Santa Ana, the Orange County district. And within the Santa Ana area, they have about 400 monitoring wells. But in this case, in this study, we're only going to limit it to 30 of the main wells within the basin. And so let's take a closer look at one of these wells here that's sitting right in the middle of the Santa Ana basin. And let's look at the hydraulic head time series. So what I'm showing here is hydraulic head for the 3 different aquifer layers. Blue is a shallow aquifer, red is a principal aquifer, and black is the deep aquifer. And so the first thing that you'll notice is that you have these large seasonal variations in hydraulic head, which are related to groundwater pumping and recharge. As you pump, you decrease the hydraulic head, and as you recharge, you increase the hydraulic head. And what you can notice that here in the principal aquifer, the amplitudes are much larger because that's where we get most of our water from. So it makes sense. Also, if you look at the amplitude of these variations, you can see that it decreases very sharply around 2008. In 2008, the Orange County folks told us is when they stopped this program that was called the short-term seasonal shift, where in this program, all the districts around Southern California were told to pump only in the summer months and no pumping at all in the winter months. And so when that program was active, we had this nice regular up and down oscillations. But when it was stopped, the amplitude changed quite remarkably, and you get so the amplitude decreased right after 2008. So also, in addition to these short-term oscillations, you see these long-term trends in groundwater levels. You see this long-term decline that stops around 2005, and then we get this uplift, or this increase in background water levels. And if you look at the rainfall data for this region, you can see that associated with this increase in groundwater levels in all aquifers, we have very high rainfall. And we'll also see how this can be affected by groundwater production practices. So for steady or stationary seasonal signals, by stationary I mean that for seasonal signals that have a constant amplitude and phase in time, the two main quantities that we're interested in, as I just said, are amplitude and phase. So we have a seasonal signal. It has a certain half amplitude or peak-to-peak amplitude if you want to. And it also has a phase delay, where a phase delay measures the time from the start of the year to the time of peak signal. So for a given time series that we measure amplitude and phase delay, we can measure the magnitude of its oscillations and the timing. We can have an idea of its timing. And so if you take the well that I showed, that we just saw, and we look at instead of 3 depths, we're going to look at 14 depths because that well has monitoring ports from about 50 meters to almost 600 meters. We get a pretty good depth resolution. And so I want you to focus on the blue curve first. So this blue curve is showing amplitude and phase for the seasonal oscillations for this particular well. And if you look at amplitude, the amplitudes are highest in the principal aquifer. So that makes sense. This is where most of the pumping occurs. So we have the highest amplitude, highest changes. And if you look at the timing, we can see we have this diffusion behavior where perhaps pumping originates here and then the pressure changes take time to diffuse away. Now if you compare this blue curve to red curve, where the red curve, instead of the seasonal signal, it's now that transient increase that we saw due to the high rainfall. So we can do that. We can play the same game. We can measure the amplitude of that increase, and we can measure the timing of when that increase had its peak signal. And if you look at the amplitude and phase for that, you can see that the timing has a lot slower diffusion speed than this seasonal signal. And if you look at the amplitude of the seasonal signal has a very rapid decay, whereas the amplitude of this slow increase seems to be more persistent in depth. So this can actually be explained quite easily, I think, if you look at if you consider 1D groundwater flow. So if you have a diffusion relationship that relates the second derivative of hydraulic head variations in space to time variations of hydraulic head under a certain source, and let's say you assume that this periodic source, you assume the source is periodic in nature, then what happens is that you get the solution for hydraulic head, the time solution for hydraulic head has this form. And if you focus on these two terms here, we have this attenuation term out here in front and a diffusion speed term. So in this attenuation term, you can see omega here. It's a frequency-dependent attenuation. So very rapid high frequency means you have very rapid attenuation, which makes sense because here in the seasonal, for the seasonal effects, it has higher frequency, so the amplitude attenuates faster, it decreases faster. And the diffusion speed should be faster for a higher frequency. You can see that for the seasonal signal, it diffuses very quickly, whereas for the lower frequency uplift increase, it diffuses much more slowly. So this will become very important when we interpret short and long-term ground deformation. So let's look at ground deformation. So here I'm showing GPS data, vertical elevation data for a GPS station that's sitting right in the middle of the Santa Ana Basin. And it's going to be right next to the station, the well that we were just looking at. So we decompose the GPS station into short-term and long-term signals. So we use the methods that I presented in the first half of this talk. These would be your long-term transient signals, and then this would be your short-term, and then these would be your short-term seasonal effects. So you can then decompose your well data in the exact same way. So now we have 14 well time series. So each well is at a different depth. You decompose it into short-term and long-term signals as well. And you can see that you have a lot of similarity here between these data. So what we want to do is we want to perform a correlation analysis. We want to find where these short-term signals are most correlated with these well time series. And so what that tells us is that we then localize the effective depth at which the aquifers are most compressible, at which they're contributing the most to to ground deformation. And when you do that, you can see that the interesting thing here is that you have different depths of maximum signal correlation between the short-term signal and the long-term signals. For short-term signals, we get the periodic GPS deformation is mostly correlated with hydraulic head variations near the aquitard layer, separating the principal and deep aquifer. Whereas if we look at the long-term signals, the long-term signal is mainly correlated with time series that are in the deeper aquifer. So you would initially expect that these would be located at the same depth, but actually they're at different depths. So we'll explain that in a little bit. But here, the assumption here is that we're assuming everything is elastic. And for the most part, what you see is that the short-term signals are elastic. You have this nice one-to-one correspondence, and same with the long-term signal as well. So now let's take a whole bunch of INSAR data that we have, 881 ERS and MVSAT interferograms over the LA basin, and we're going to put it into this magic box of ADMM analysis, and we're going to decompose it into short-term signals and long-term signals. So we saw in the GPS that this was very useful, so let's try it with the INSAR data. So for short-term signals, I'm also going to make a distinction here between repeating short-term signals and non-repeating. So repeating is a periodic, a well-behaved periodic signal that has a constant amplitude and phase. And that's a pretty good assumption prior to 2008, which is when that short-term seasonal shift program ended. But we can also reconstruct non-repeating signals as well. And then we'll look at long-term signals separately. So we first look at repeating or stationary seasonal signals. We can measure, we can have an amplitude and phase for each pixel in our INSAR time series, in our INSAR time series model. And so here on the left is the seasonal peak-to-peak amplitude that we get for our data, and on the right is the seasonal phase delay. And if you look at the amplitude, we have very good resolution here. You see that we have this concentrated zone of high amplitude located here in the Santa Ana Basin, but we also have these two peaks here closer to Long Beach. And we have a very striking line here where the amplitude goes to 0, and this is basically due to the Newport-Inglewood Fault, as mentioned before. This is barrier to fluid flow, so as groundwater is flowing, diffusing outwards, it's going to hit the Newport-Inglewood Fault, and the amplitudes go to 0. If you look at the phase delay, as I just used the word diffuse away, you can see that in the center of the basin, the ground deformation peaks earlier, so that it peaks in the center of the basin. You have these seasonal signals that start moving and then diffuses outwards towards the margins of the basin. And to get a better idea, first of all, we can then compare the ground deformation to phase delay for GPS and well data. So well data is shown here in these diamonds, and so the color scale is exactly the same. So if you look at the well data and you look at the phase delay for the well data for the WRD and the Orange County stations, you see that you have a very good correspondence between ground phase delay and hydraulic head phase delay. So basically, this diffusing that we're seeing is primarily due to diffusion of groundwater. So as groundwater diffuses away from these pumping areas, then the corresponding seasonal deformation also diffuses away with the same phase delay. So this reinforces this elastic relationship that we have between hydraulic pressure and ground deformation. And to get a better sense, just visually, of what's happening, if we look at ground deformation, this is the seasonal ground deformation. You can see that the ground within the basin is pretty much moving out of phase with the rest of the ground, which is probably responding mainly towards earth tides or oceanic tides. And you can clearly see this diffusion effect where the center here is deforming first, and then the deformation diffuses away. So you can see quite clearly the zone of high amplitude here, and these two zones of high amplitude here. And you can see the effect of the Newport-Inglewood Fault acting as a barrier to fluid flow. What you can also see here is that if you look here, we have pretty good spatial resolution of this feature here which looks just like a discontinuity, which looks just like a fault. And so in my thesis, I go through some simple 1D diffusion simulations, and we think that this is probably most likely an unmapped fault that wasn't known before. So that just goes to show you what INSAR time series can provide you, because it has very high spatial resolution over, let's say, GPS data. So now if you assume that the seasonal signals are not steady, they're not stationary, and we want to measure something that's time-varying, instead of using these periodic terms that are sines and cosines, what we can do is we can model these time-varying seasonal signals as sum of B-splines, which is different from the integrated B-splines that we used before. So if you use the sum of B-splines, you can get these non-steady seasonal signals that have changing amplitude and phase. And so if you look at a point here in the Santa Ana Basin, if you look at its time series, you can see that before 2008, it has this nice up and down seasonal motion that we saw before. But right when 2008 hits, if you look at the ground deformation, basically the up and down motion almost disappears completely. So it's quite remarkable to show that these groundwater management practices by Orange County and the WRD, they're reflected very well in these time series that we're seeing. So it just goes to show you how much of an effect that groundwater management has on ground deformation. So now if we look at the long-term subsidence, what I'm going to be showing here is an animation between 1995 to about 2003 to 2004. And what we're seeing here is that mainly within the basin, we have this really widespread subsidence signal. Most of this basin is subsiding from 1995. And this signal is actually more widespread than the seasonal signal that we saw before. The seasonal signal was kind of concentrated in this band right around here, whereas the subsidence signal is more widespread. And it's really localized here in Santa Ana Basin, and also, well, it's mainly localized here in the Santa Ana Basin. Well, we can also see we have these other uplift effects here. So here is quite interesting. It's called the Santa Fe Springs oil field. So they've decreased oil production here, and what's happening is that the ground is now uplifting. And so you have this simultaneous long-term uplifting event that happens with a different time scale than the subsidence event. And we can also have some subsidence here. This is in the Wellington oil field near Long Beach due to oil pumping. So the one factor that I haven't mentioned yet is groundwater pumping. How is this related to deformation? So if we look at the amplitude map, the seasonal amplitude map for ground deformation, and compare it to the seasonal amplitude of pumping, so what's my average pumping? So these are large-scale production. This map was formed from large-scale production wells given to us by Orange County. You can see that where pumping is highest is where you get the highest amplitude of ground deformation. Same here. These two zones where we have high amplitude are directly corresponded to two zones of high pumping within the confined area. So in other areas where you see there's high pumping, this is in the unconfined area. So the water table can move up and down, and we don't see it in the ground deformation. So everything pretty much makes sense here. High pumping leads to high seasonal pumping leads to high seasonal ground amplitudes. And in the long term, what I'm showing here in red are long-term production rates, the background production rates. So in this case, I have increasing downwards here. And if we compare that to this blue curve here, which is integrated basin deformation, I'm doing an aerial integration of total deformation within the basin. What you can see here is that steady increases in groundwater production are what's causing this subsidence signal that we see within the basin. So as we increase our groundwater production, we have this elastic response to it, and the basin deforms. And then here, when we had that uplift event that was due to rainfall, we can see that it's not purely due to rainfall. It's due to rainfall and also a decrease in groundwater production. So the joint groundwater production and rainfall, those are our two inputs to the system. As they change, we can see it change quite clearly in this deformation. So lastly, I want to show remind you that, remember we did this correlation analysis between ground deformation and depth of hydraulic head time series. And we saw for that one station that the depths of maximum correlation were different. So if we do that, we repeat that analysis with our INSAR data. So INSAR now gives us, now allows us to compare ground deformation to all wells because we have a continuous map. And what you see is that this background color is showing you the depth of the aquitard, that the depth of best correlation for the short-term signals are basically at the depth of the aquitard or shallower. So it's basically responding to the seasonal pumping, the seasonal groundwater production. Whereas if you look at the long-term signal, you have this systematic effect where a lot of these wells are actually deeper than the aquitard. So it's reinforcing this result where the long-term signal is mainly due to long-term changes in the deep aquifer. So this can actually, I think this can be explained by going back to this figure and this equation here, where we looked at how the different timescales diffuse in depth. Then basically, these seasonal variations, they have a higher temporal frequency, faster diffusion speed, but they also have more rapid amplitude attenuation. So for these rapid seasonal groundwater pumping and recharge, what happens is that the pressure perturbation is confined to a limited zone because of this attenuation. And so then that the compaction of the aquitard, which is adjacent to the principal aquifer, that's the one that's contributing most to ground deformation. Whereas these long-term variations, we have lower frequency, so less attenuation. These longer-term variations are due to, because the pressure change is now able to traverse greater depths of the aquifer system. And so you get a greater pressure change in the deep aquifer, and perhaps the deep aquifer has a higher clay content, so we see some high compressibility of the deep aquifer. So in conclusion, in the first part we saw that efficient transit detection can be performed by estimating the coefficients of a dictionary of B-splines, which would integrated B-splines, which look like transit signals. Sparsity promoting regularization localizes the timescales and onset times of signals. And we can use simultaneous time series modeling of all INSAR pixels or all GPS stations at once using this ADMM massively parallelized algorithm. And when we applied it to hydraulic head, GPS, and INSAR data, we were able to reveal very complex ground deformation that was due to very complex groundwater flow in these aquifers. And we had good correspondence, though, between our hydraulic head and ground deformation. So an analysis of the short and long-term signal suggests some kind of stratification of deformation, of compaction, where different parts of the aquifer system are contributing to different timescales of ground deformation. And lastly, we see no large-scale evidence of subsidence due to inelastic compaction. So at the moment, it looks like the groundwater practices are still within sustainable bounds.